fuzzy numbers. Yeah.
Yes, sir. Thank you, sir. We had such an interesting session, sir. Thank you. Thanks a lot. So, Dr. Gupta started with the meaning of fuzzy as uncertainty and then defined intuitionistic fuzzy set, intuitionistic fuzzy numbers, and how to compare fuzzy numbers. Then application of these numbers in transportation, fuzzy transportation problem. Thank you, sir. Thanks a lot. Thank you, everyone. Bye, everyone. Have a nice
Thank
day.
you very much. Thank you.
Thanks, sir. Bye, sir. Take care.
Thank you, sir.
Thank you, sir.
Thanks to the organizers for having given me the chance to serve as chair the session. Thank you, sir. Thank you, Madam Srisha, Madam also.
So I thank Dr. Shivkumar Gupta garu for his excellent talk and Dr. R. Parvati garu for chairing this session. I now welcome Professor J.S. Rao garu from University of California to this e-seminar. And I invite Professor C. Umashankar garu to chair the middle censoring and application session and introduce Professor J. Srinivas Rao garu to the participants. Professor Sri Umashankar garu.
You're able to hear my voice, sir?
Yes, sir.
Yes,
We
sir.
are able to hear.
Yeah. Good evening, Sharma garu. Okay. So shall I start, sir?
Yes.
Yes, sir. You can
Shall I start my introduction?
Yes, sir. You can go ahead, sir, please.
Right. So it's my pleasure always. And really I'm privileged today evening to rather introduce a great statistical, say the statistical thinking legend, and once again the first student of a legendary personality of Professor C.R. Rao. And this is a very apt that he is coming on this valedictory address here at the session. And I'm very, very happy that whenever we meet, it's a sort of learning. Always the time you spend with Professor Rao is a sort of learning process always with him. So it's my immense pleasure to introduce Professor Srinivas Rao Jammalamadaka. He is among the leading researchers in statistical science during the last 5 decades. Author of 3 books and has about 200 publications. His research, scholarship, and professional services have had a great influence in the theory and applications of statistics. Professor Rao Jammalamadaka earned his PhD, MStat, and BStat degrees from the Indian Institute of Calcutta, India. He started his academic career at the Indian University before joining the University of California at Santa Barbara in 1976, where he has been honored with a distinct professorship at the University of California. Professor Jammalamadaka achieved international reputation for pioneering work in developing new tools to analyze nonlinear phenomena like directions and circularity. He has held various positions in various universities, including the University of Wisconsin, University of Leeds, Uppsala University, Sweden, Indian Statistical Institute, Calcutta, Indian Institute of Technology, Mumbai, Chalmers Institute of Technology, and Gothenburg University, University of Himalaya, and the Australian National University. He is the founder of the Department of Statistics and Applied Probability at the University of California, Santa Barbara. He has been heading the department right from 1989 to 1993. For his pioneering contributions to statistical theory and applications, Professor Jammalamadaka received various awards and medals. He has been elected as a fellow of the American Statistical Association, the Institute of Mathematical Statistics, the Institute of Combinatorics and Applications, the C.Y. O'Connor Fellow of Cotton University of Technology, Perth, and an elected member of International Statistical Institute. He has been awarded an honorary doctorate of the Swedish University of Agricultural Sciences in 2014 in partial recognition of his a wonderful job of leading about 45 PhD students at the University of California. He has been honored with Outstanding Graduate Mentor Award, and many of his students are working as academicians and as statistical practitioners in various organizations all over the world. He has been an invited speaker at more than 300 national and international statistical meetings all over the world, and topics including problems of weak convergence, directional and non-parametric statistics. He has been a member of editorial boards of statistics and probability letters, modeling and applications, Journal of Non-Parametric Statistics, and Journal of American Statistical Association. I just very recently, I'm very happy that the made him as an adjunct professor as per your university is concerned. And it is my fortune once again to have such a wonderful personality. And really, I do not know how far I am eligible to chair the session of Professor Rao, but still the privilege has been given to the GITAM University, and I am very much thankful to the administration and the chairman and the wonderful faculty of GITAM University. Today is going to present a talk on middle censoring and applications, and this is really connected with the survival analysis, where there is considerable literature which treats data that is censored from right, left, and both. In his talk, he considers the situations where the data becomes unobservable if it falls inside a random interval in the middle. This happens in clinical trials and lifetime studies where a subject is temporarily absent or withdrawn from the study, and the event of interest occurs during this period, so that the exact time of occurrence cannot be observed. Both left and right censoring are special cases of middle censoring. So he comes up with a wonderful analysis of his own, and he is going to propose a methodology in order to get over the solutions. And it will be a very interesting and a very practical in which this particular area will be applicable as far as the statistical science is concerned. And sir, once again, it's my privilege to invite you to the dais. And it is Professor Rao Jammalamadaka. Professor, no.
Thank you, Umashankar. Thank you for such a long and introduction about me. You guys can hear me now, right?
Yes, sir.
You can all hear me, okay?
Yes, sir.
Yeah,
Yes,
I'd
sir.
like to thank Sridhar and Sirisha to have persuaded me to give a talk in this forum. My talk is somewhat disconnected to what you guys have been listening to all this time. But my hope in presenting this talk is to see if one of you can jump and say, there are some connections. We can work together on this topic. And my talk is statistical and probability oriented, but you will perhaps see that maybe some of you will see some connections here. Okay. Do you get to see my slides now?
Yes,
Do
sir.
you get to see the slides?
Yes, sir.
Okay, good. I want to be sure that everything is good. I call this talk middle censoring and revealing hidden information. That's what we all try to do. Basically, sometimes the information is hiding and we need to figure out what it is that we can make out of hidden parts of the data. And as Uma already mentioned, I'm at the Department of Statistics, and I also have been recently affiliated with GITAM at Vishakhapatnam, where you guys are all. So I have double affiliations that I'm mentioning. And I'll mention the problem of what the problem is, what people do when there is no censoring, meaning all the data is available to you, and what is the censored case, what is the censoring applications.
Full screen mode.
Sir, can you?
Full screen
mode, sir.
Call me full screen? Okay, let's see.
View,
View, sir.
view, sir.
View, go to view and full screen, where is that? Right.
Control F.
Yes, sir. Yes, sir.
Okay.
Thank
Yes,
you.
fine, sir.
Now I'm
Absolutely
fine. Okay.
fine, sir.
Okay, thank you. Applications, and I'll tell you what the solution is to this so-called middle censoring problem. And I'll make some remarks and then give you illustrative examples and a set of references to this topic. And here is what the problem is. In statistics, we start with what we call a random sample. x1, x2, xn is a random sample from an unknown distribution, f of x. What is usually, you don't know what the model is from which the data came. And these random sample is what probabilists call independent, identically distributed random variables with the cumulative distribution function. This is the basic tool in probability. For any random variable, the cumulative probability until a small x is denoted by capital F of x. This is called a cumulative distribution function, capital F of x. And this is my goal, to figure out what this capital F of x is. Given a set of observations, x1, x2, xn from such an f. Okay, for any x in R, this is a function. This is a function on the real line. And so the goal is to estimate the CDF, this cumulative distribution function, from the data x1, x2, xn. Or sometimes one is interested in its complement. Complement is the 1 minus f of x. What does that represent? That's the probability x is bigger than x. This is x below x, and this is x above x. This is what one calls a survival function, because if x is the lifetime of an individual's or a machine component or electronic component, we're asking, what is the chance that this item will survive beyond a point small x? So that's called, it's called a survival function, but it's the same thing as capital F of x, 1 minus f of x is called a survival function. So my goal is, given an x1, x2, x in a random sample, find this capital F, or find the 1 minus f, this is your survival function. And now this is done, I will just give you a brief summary of what people have already done over the years. And this estimate of capital F is obtained by so-called empirical distribution function, EDF, I call it. What does an empirical mean? Based on the data. How do you estimate the distribution function based on the data? This is how we do it. We ask, what is after all capital F of x? Is the cumulative probability till the point small x. So I ask myself, how many of these observations are smaller than x in the sample of n, right? This is a proportion 1 over n. N is the size of the sample. I going from 1 to, this I is the indicator function. This is 1 if xi is less than or equal to x and 0 otherwise. So what am I doing for any small x? I'm finding out how many of the x1, x2, xn are less than x, small x, and then taking a proportion. So it's a step function. It climbs up with small x. And this survival function, this function CDF has, this is called the non-parametric estimator. Now, in fact, most of what I'll talk about is in statistical inference, people start by assuming some models for the data. x1, x2, xn comes from a normal distribution, binomial distribution, and then say something about the parameters of the model. That's called parametric inference. But what I'm focusing right now is to estimate the whole distribution function. These are non-parametric, no parameters involved at this point. Okay, and it's known that this empirical distribution function fn of x goes to f of x pointwise for each x. These are results that I won't. I'll just tell you some known facts. Fn of x goes to fx uniformly in x. It's called the Glibenko-Cantor lemma. So the fnx actually is a good estimator for large n as n goes to infinity. These are called consistency results. So the sample-based distribution function fn of x that I described here converges to the true distribution function uniformly in x. And that's a good thing to know. And root n times fn of x minus f of x, fn of x is a random quantity. This quantity is what we call a stochastic process. For x belonging to R, if you look at the difference between the sample distribution function fn of x and the true distribution function f of x, the difference, if you multiply by root n, this whole thing as a process on 0 to on the real line converges to what's called a Brownian bridge and so on. So these are all known results, and that's just to give you a brief outline of what people do. when the full data x1, x2, xn is given to you. Okay, now you know what happens oftentimes. Right censoring occurs when xi, say the lifetime, is censored by a random censoring time yi. Say the time when a patient leaves the study. Let me explain. Think of this x1, x2, xn as lifetimes of a patient's undergoing some treatment. Again, xi is the lifetime, when does the patient die, ith patient die, and xi denotes that lifetime. And then what happens is you're studying n such patients, x1, x2, xn. If you have the full data, you do what I was telling you on the last slide. If you don't have the full data, sometimes what happens is a patient that you are studying leaves the town, goes to America or someplace. So what happens then is you don't have xi value anymore, right? But then what happens? It doesn't mean you don't have any information. When did he leave to USA? Yi. And then you know he obviously went to USA with a life of his own, right? So in some sense, xi is certainly smaller than yi. Yi is the time he left. So obviously he was living at that time. So we at least note the fact that he has left town at the point yi. So what do we observe? We observe this value zi, which is the minimum of xi yi, either his lifetime or the time at which he left, in which case is bigger than yi, right? So this is the missing information now. This is what's called censoring. Censoring to the right. And I'll tell you a bit more about different kinds of censoring before I move on to middle censoring. And you also get to see, I also tell you a value delta I, which is a 1 if zi is a xi, that means it's the true lifetime. Zi is the value of the minimum of xi yi, and delta is a 1 indicating that this zi is actually observation. And delta is a 0 when zi is a yi. That means delta I takes the value 0 when the observed value is not the lifetime, but the time at which the patient left the study. And there is a celebrated Kaplan-Meier estimator. It redistributes the mass corresponding to the censored points to those uncensored points on its right. And this has been studied extensively. So what does one do in a case like this when there are some xi's, some are yi's? So the typical idea here is, if you notice, each xi gets a weight of 1 over n in the uncensored case. So what happens is when someone leaves the study, so what we do is we take, you think of, I had a professor named D. Basu, famous name in statistics and probability, and he would describe probability as an ounce of gold. So each patient gets 1 over nth portion of the gold. So when someone leaves the USA, we say, give me back your gold and give it to the rest of the people in the study. That's what the Kaplan-Meier estimator in a nutshell does. So what's going on? If someone leaves the study, his or her amount of gold, 1 over n, is distributed to the people who are still in the study at that point. Okay, that's the Kaplan-Meier estimator, and is very famous and well known. And left censoring is similar when a point xi is censored if it is smaller than a yi. So this is called left censoring, as you can. And then there are people who studied what we call double censoring. When an observation gets censored to the left as well as to the right. Observation xi is censored if it's to the left of a random li or to the right of another random ri. This can happen, when people enter the study after, not the people, but I'm talking about not lifetimes anymore, but the components that you're studying. Maybe the component's already dead by the time you start to watch it under study. So then it's less than li, you can't see xi, and then is also censored if it's to the right of ri. Okay, so now those are things that have been around. So now this is where I come from. A new concept that I would like to discuss is called middle censoring that I helped introduce in 2002. The idea is as follows. Middle censoring occurs when an observation xi becomes unobservable if it falls inside a random interval, li to ri. Li for the left limit, Ri to the right limit. Think what's happening. If an observation xi falls in this interval Li to Ri, I drew a graphic here before you read all this. So if xi falls in Li to Ri, I don't get to see it. If it is to the left of Li, I see it. If it's to the right of Ri, I see it. So this is called censoring in the middle. So one sees the actual value of xi only if xi is to the left of Li or to the right of Ri. And xi falls inside this interval, we only note that fact. This is important. At that point, we know there's one observation in between Li to Ri. And this idea generalizes both left and right censoring. Since Li can be set to minus infinity, Ri can be set to plus infinity, I'm saying this middle censoring idea where you censor in the interval Li to Ri, that's a very general concept. It generalizes the left censoring that Kaplan-Meier discussed, right censoring, and the left censoring and things like that. So again, are you with me that we have xi becomes unobservable if it falls inside a random interval Li to Ri. Li is always less than Ri. Now, when does this happen? I'll give you applications. This is maybe that's what I'll give you. In example one, children are being observed as to when they first start to do a certain activity, like walking and talking. In a hospital in Africa, children are being observed. When do they start walking? Okay, due to some external exigencies like war or a strike, the hospital where daily observations are being taken was closed for 60 days. And for those children who started the activity during this period, the actual time cannot be observed, except that we know the interval during which this occurred. So what happened? The hospital closed for 60 days. So if a kid starts to walk or talk or do this activity of interest, then we only say, well, this kid did it during those 60 days. I don't know exactly when. Okay, so if they did it before the hospital closed, so this is interesting. This happens oftentimes, like a machine. You know, you're observing the lifetime of a certain electronic components. You start burning them at some time, and then you observe when each of the component fails. That's the lifetime of the electronic component. And then you go on a vacation for 10 days, okay? And you're not observing the lifetimes during that time. You come back and find certain components that were alive before you left on vacation are now no longer, they're dead, they're failed. So that is the kind of thing where middle censoring occurs. Middle censoring is when some of the middle parts, in this case, I want you to observe these 60 days, although I say a particular 60 days, they are random with respect to the birth day of the individual child. So they are random intervals for each individual, for each child. So this follows my scheme here. Li to Ri, if xi falls in between, I don't get to see it. But the point is, here is a talk I gave at GITAM some time ago. And I'm interested in something called directional data. Directions are can be thought of as on parts of a circle. And then people, at least in the past, in ornithology, they would watch which direction are the birds flying. They would release a bird at this point on a tall post, and then they watch which direction are the birds flying. And if the birds happen to be going behind a cloud or behind a mountain, something, you know that the bird flew in between this interval, in that bracket. In this interval, you only know one bird flew in there. You don't know exact value for that particular flight, what direction the bird flew. Okay, so the bird disappeared behind this hill or whatever. Okay, so there are several interesting examples. Middle censoring appears to be complementary to double censoring, but not really. You have to think about it. Double censoring is when you lose on the left, lose on the right. Middle censoring is when you lose in the middle, but it's not really complementary except in what I call compact homogeneous spaces. The censoring interval can be generalized to the union of intervals or any random set. And theoretically, it can be in any higher dimensional space, such as in spatial statistics. So the censoring might be that you don't observe certain parts of the space. And such generalizations are not yet explored in any detail. So middle censoring can be where you don't get to see something in the middle of what you're observing. Okay, in the real line is an interval that you don't observe. Okay, now, I don't know how much detail I will get into, but let me see. So X1, X2, and are IID from a CDF of interest, capital F of subscript X on R1, while the censoring intervals L1, R1, Ln, Rn, for each Xi, there's a potential censoring interval. And if Xi falls in this interval, then it's lost. We only get to see that is between L1 to R1. And there is its own CDF cumulative distribution function L comma R, and we might call it a G. Okay, and then assume that Xi's are independent of LIRIs. In other words, the actual values and the intervals don't, like for example, I was saying the cloud, where the cloud is, the cloud doesn't move depending on the bird's path. So LIRI is independent of Xi. So here what we have is something similar to what I was describing on right censoring. I get to see delta I, which is the indicator function that Xi belongs in this interval. If Xi doesn't belong in this interval. If Xi doesn't not belong in this interval, it's a 1. That means you actually see the actual Xi. And if this indicator takes the value 0, if Xi falls in this interval, and that means Xi is censored. So the values Zi we see are of two types now. Xi's, if delta is 1, the actual value, or an interval, Li to Ri, if delta is 0. This is where I call, when I was giving a talk like this, someone said, this looks like fuzzy data. In some sense, some of the data points are lost in this interval. So this is where my idea of trying to address it to you, to see if you see a connection to observing X1, X2, Xn, all of them is the uncensored case. Now in my case, I see some Xi's actual values and some intervals. What does this interval signify? That Xi fell in between this. Xi is some value in between this. What the interval is this? This is a random interval. And then I get to see Zi's. Zi's automatically tell you if it's an actual value or an interval. So you see Zi's or Zi delta I, that is the available data. So this is the problem. Estimate Fx based on the data Z, vector Z. So that's where we are. Originally, I was telling you the empirical distribution function estimates the data if you have all X1, X2, Xn. But now I want you to estimate the same distribution function, cumulative probability below small x, based on the data Z. Z consists of intervals and actual values. Okay, so that's the problem. That's what a middle censoring problem. And if you do this, well, okay. I shall persist. This idea can be found in F. There is something called self-consistency equation. Self-consistency, there's a nice paper by Brad Efron in 1967 and a few other papers on this topic of self-consistency equation. Brad Efron, by the way, is the one who got International Statistics Prize the last year. He is the second one to have obtained this, what we call the Nobel Prize in Statistics. And the one before that went to David Cox, D.R. Cox, and so on. C.R. Rao, we are hoping we'll get it this side. But okay, any case, going back to Brad Efron, he introduced this idea called self-consistency equation. What is that equation? You start with an F hat is said to be a self-consistent estimator. I'll keep writing it as self-consistent estimator of F. If it is a solution to the self-consistency equation. What is this self-consistency equation? You start with some Fn, the empirical distribution function for the uncensored data. You remember some of the Xi's are uncensored. Use them to estimate the Fn. That's not all the data. But use that data and then take a conditional expectation of that function with respect to given Z, given the data that you have. The data that you have is Xi's and LIRIs, the intervals and individual points. So if f hat is such that this happens when you do the conditional expectation, and then you get the same f hat, then that's called self-consistent estimator f hat. If we start with f hat being the true CDF, then we get f hat as the conditional expectation. This has the flavor of Rao-Blackwell theorem, although it has no parameters or sufficiencies involved. This is the data. This is an estimator of what we want to estimate. So we are doing conditional expectations, and that's what Rao-Blackwell theorem has something to do with that. Okay, now more to the point of the solution of the self-consistency equation is obtained iteratively. So what we do is you start with some fm hat and get f hat m plus 1. If you do this conditional expectation, I'll tell you how we do this. So you start with this of f and f in both places. You start with some iterative procedure, some initial estimate, and then you get the conditional expectation. We call it the improved estimate. And this is the equivalent of the EM algorithm. EM is the expectation maximization algorithm. And okay, now I will tell you what this results in. The self-consistency equation gives me this star. This is something to, this is how we estimate F that I am interested in. What is this estimate? It says, you remember your delta I. Delta is 1 if actual xi is observed. If for a given t, if actual xi is observed and if that xi is less than or equal to t, it counts as a complete weight of 1 over n for that xi. Let me repeat. Delta is 1 if actual xi is observed. And I'm trying to find out the cumulative probability until the point t. If the actual xi that you saw is less than or equal to t, meaning delta is 1, then it counts 1 over n. On the other hand, if your thing is censored, if the observation is censored, and the right limit of Ri is less than or equal to t, then it counts as also full weight. What does that mean? This I'll explain it in the next page, next slide. And if 1 minus delta, if you censored value, and if your t that you are trying to find the CDF at belongs in this interval Li to Ri, then you have to apportion the f hat in this fashion. So it's an interesting equation. Self-consistency equation riddles in something like this. And this is how you count xi's when delta is 1. How do you count ri's? I'll tell you about the second term in a minute. And if t falls in this interval, and you're trying to find out how whether the xi is less than t or bigger than t, then you have to apportion like so. I said this. It's easy to interpret the 3 terms on the right-hand side of the star equation. First term says uncensored xi gets the full weight 1 over n. Second term says even if an observation is censored, if Ri is less than or equal to t, making the whole interval to the left of t, then clearly the corresponding observation is to the left of t. Whole interval is to the left of t, then it gets a full weight 1 over n. The third term says to apportion the probability carefully if t belongs in Li to Ri. So those are the 3 terms that you get. So now, you know, that equation, there is no explicit solution for this f hat. I'm trying to estimate the whole function of the real line. For iterations, there's the EM algorithm. We replace f hat on the right-hand side by f hat m, and f hat on the left-hand side by f hat m plus 1 in equation star. So in this equation, I go back. Okay. Okay. Anyway, this is, you can do this iteratively, and I mentioned here, in the simpler right-censored case, Kaplan-Meier estimator comes out as the explicit solution for this equation, and no iterations are needed. So I'm trying to rule off Kaplan-Meier as a special case of what we are doing. Kaplan-Meier is a big celebrated right-hand censoring case, and I'm saying we have a more general case here. The iterations needed to solve f hat are easy to implement for any data set, and one can write a simple program that will do this. We have such programs that can tell you how to get an f hat. So such an f hat, we'll call it f hat n based on data n, all the data points. Data points are intervals as well as actual values. So such an estimate that we get through iterations is what we'll call f n hat from now on. Now, SC being the result of convergence of the EM algorithm, it only provides a local maximum of the likelihood equation, may not be unique. There are these all properties of the EM expectation maximization algorithm. And but we show next that the NPMLA, this is something I'm going to say very briefly, non-parametric maximum likelihood estimate. You see, there are methods for estimating the, most of you who did statistics would know maximum likelihood estimates. What we do is you maximize the likelihood function with respect to parameters. But there are such things as a non-parametric maximum likelihood estimates because I don't have any parameters. I didn't mention in theta so far. I mentioned only capital F. You can estimate capital F, and that's called the non-parametric MLE, which can be shown to be unique and also comes from solving the same equation. So that's neat. So the self-consistent equation star that I gave you is also the result of NPMLA. Now, you know what? I'll very briefly tell you how one writes the likelihood function. So F denotes the set of all CDFs on the real line. The likelihood for any F in this script, this thick F, given the observed data, is given by this L of F. See, usually likelihood functions, you write L of theta. But for me now, I'm trying to estimate the capital F, which is one of the CDFs. Look at this set of all possible CDFs on the real line. And you see what I wrote here? This is quite trivial. This is, if delta is 1, I'm looking at the mass at the point xi. And if delta is 0, that means I have an interval, then the value is the probability of such an observation is FRI minus FLI. The XI falls in between FRI and FLI. So if you followed that, that's about all that you need to know. So the delta is 1, XI is the value, and that is the probability of that XI. And if delta is 0, XI is not available, is in the data point falls in between Li to Ri, that's the probability of interval Li to Ri. So that is the L of F. How do you find a maximum for such a function over capital F? Well, you can write down the log F, 1 over n log F, that's not a big deal. So from here, so I'll tell you very quickly, there is something called, cancel, okay. What the hell is going on? Okay, okay. Okay, now I hope we don't lose anything. Okay, so it turns out there is a ATX, and you have to maximize F of in the direction of AT. You have to maximize this phi function. Phi is the log likelihood I mentioned to you earlier on. So ATX is defined here. I don't necessarily want you to digest all this in one loop. There's a paper by Gronobohm and Wellner, and you maximize the phi of F by looking for the derivative of phi of F with respect to F in this particular direction. It's called a Ghetto derivative. Frechet derivatives and Ghetto derivatives, those are functional derivatives. So you need to do that. And if you do that, after some simplification, the solution F hat is identical to the one satisfying star. In other words, the NPMLA equation is the same as the self-consistency equation, for which we discussed an iterative solution. So what I'm trying to tell you is, although Efron and such people said there is something called self-consistent equation, I'm saying you can go one step beyond that and get so-called non-parametric MLE of the capital F, and that matches exactly the same thing. It can be seen that the NPMLA puts all the mass of on the uncensored observations. So you see, we have some uncensored observation, actual observations xi, and some intervals. So it turns out the NPMLA puts all the mass on the uncensored observations, except when a censored interval contains no uncensored points. Words seem a bit confusing, but what I'm saying is there may be some censoring intervals with no uncensored points inside there. I'll give you an example in a minute. Okay, so and maximum likelihood estimates always put the mass on the uncensored observations only, except You have a censored interval and it has no points inside, no uncensored points inside, but we know a censored interval has a point somewhere. So when this happens, the mass corresponding to this interval may be assigned to the midpoint of the interval. You remember, we have an interval, we know there is a point, put it in the middle of that interval for now. Thus, in the iterative procedure, the initial estimate may give equal mass to all the uncensored observations and to the midpoints of those censored intervals which contain no uncensored observations. In other words, I'm saying you have to start with an iterative procedure, you have to start with something. The way you start it is to give equal mass to all uncensored values and to the midpoints of the uncensored intervals if they don't contain any uncensored observations. I'll give you a very simple example here. Let's see if we follow this. This is as simple as this. We just have 5 observations. I have 3 of them are actual values, 2, 4, and 6. They are uncensored. I see the actual values. And some are 2 are intervals, Z4, Z5. I know one of the observations between 1 and 5. I also know there is another interval in 3 to 7. See, my Z's can be either actual values or intervals. And now, question. Each of the censored intervals, 1 to 5, each censored interval contains at least one censored observation. 1 to 5 contains the value 4. Interval 3 to 7 contains the value 6, right? So what is the NPMLA says? NPMLA says concentrate your mass on just the 3, Z1, Z2, Z3. That's the, I skipped I mentioned the answer, but the NPMLA says for us to do this. If your censored intervals contains a point like 4, then only put a mass at the point 4. Point 4 already gets its own mass, but you get additional mass because of this interval. And 6 again also gets additional value. And so there are only 3 points that get any mass. So that's interesting. If you have a regular 5 set data, then each of them get 1/5, 1/5, 1/5, 20% weight on each of the data points. But now I have to do something quite different because I'm told I have 5 points, but 2 are actual values, 3 are actual values, and 2 are intervals. And now my theory says you only have to put mass on the Z1, Z2, Z3. Let's call them P1, P2, P3. I'm making life as simple as it can be. So I can write down the likelihood function on Z1, Z2, Z3 and figure out what this P1, P2, P3 must be. That is the maximum likelihood estimate of in this particular case of the CDF. So this is what happens. This is your likelihood function I wrote a bit earlier. Fxi minus Fxi minus 1 to the delta I. So there's a P1 for the first value 2, P2, P3. Those are the 3 values. And then this intervals 1 to 5 interval has 2 and 4 inside that. 1 to 5 has 2 values, 2 and a 4. Where are the 2 and the 4 are both inside here. So P1 is the value there, P2 is the value there, P1 plus P2 is the probability associated with this interval. And similarly, this is the value associated with this interval. I'm religiously following the likelihood function. And since P1 plus P2, P3 is 1, the roles of P1, P3 in this equation are interchangeable. So we put P1 is equal to P3 is X, and P2 is correspondingly 1 minus 2X because the P1, P2, P3 add up to 1. So we reduced it as simple as it can be. We need to look at the equation X square. Where is X square coming from? X, and 1 minus 2X. And 1 minus X, 1 minus X for those. So that is the equation. You want to find an X. And you become simple algebra now. So it turns out the solution of X is 0.2769. So what is the summary of all that I'm saying? The weights on the observations 2 and 6 are 0.2769. And the weight, while the weights on the observation 4 is given by 0.4472. So that is how the weights are distributed. It's quite so we know there ought to be 3 values that get weights, it's 2, 4, and 6. while 2 and 6 get points 2769, 4 gets a lot of additional weight because it's contained in here, is also contained in here. It's grabbing some more mass from the other intervals. That's amazing. In some ways, only 3 points have any value in this kind of a situation. And so this is how the likelihood maximization occurs. And this is how. Now, I did a simulation study. I'll go on for another 10 minutes and try to wrap up. I did a simulation study in which xi is exponential with mean 10, from which we generate 100 observations. Exponential distribution with mean 10, we have simulations we can do. So we generate 100 observations. These are then middle censored with Li is exponential with mean 5. Interval bits Ri minus Li exponential with mean 5. So in other words, I have to simulate it. I have to make up my own story. So Xi's are the original observations, 100 of them. I generate from this data, that model. Now this is a parametric model now. And then Li's are exponential, and the Ri minus Li's are exponential. And then if you do this simulation, from the original 100 observations, 22 become censored. What does that mean? 22 of them fall inside this intervals, corresponding intervals that I generated. For each xi, I generate a Li, Ri. And then see if my xi falls in there. If so, I drop the xi and, latch onto the interval. So 22 are intervals, 78 are actual data points. And then this figure shows the self-consistent or NPMLA, Nonparametric MLA, the Fn hat minus F0. F0 is the true CDF, exponential CDF. See, that's the black line is the true exponential cumulative distribution function. And the red line is the estimate that I got after I do middle censoring. What is that I did? I have only 78 points instead of the 100 points. And 22 of them are intervals. And then I apply my technique. What's my technique? I give you a self-consistency equation and that NPMLA equation. So there are algorithms that will do this. This is how close they are. And the sup over T over the Fn hat minus F0. F0 is the true CDF. This is my estimated CDF from the non-parametric MLE is 0.08. It's very, very close, which is surprisingly close when compared to the original Kolmogorov-Smirnov distance based on the complete data. If I take the original data, all the 100 observations, the difference is 0.07. What is the difference between the Fn and Fn hat? Fn hat is my middle censored data estimate. This is the estimate assuming there's no censoring whatever. All 100 observations are available. This is called the Kolmogorov-Smirnov distance, empirical distribution function minus the true CDF. And so that is how close they are. And we have done many other combinations of distribution for X, distribution for LR, including exponential, gamma, Weibull, uniform, and so on. In all these situations, the NPMLA, when I say NPMLA, Fn hat, that is the one obtained through iterations of that star equation star. And in all the NPMLA for middle censored data is in pretty close agreement with the Fn, the EDF, the empirical distribution for the full uncensored data. So that's it is an example, but I'm saying this is not just a one example. This happens all the time. And that means our estimates are good. And then we applied our technique to an actual data set on melanoma survival. This is in one of the standard books. Odense University Hospital in Denmark. Melanoma is a skin disease, and we have this collected survival data on melanoma. The sample contains 205 data points ranging from 10 to 55, 65. These are the days of survival after the problem. The data were censored by a random interval whose left end was an exponential random variable with mean 2000, and the width was an exponentially distributed mean 1000. You see, they didn't have censoring. I did this censoring. Originally, they had 205 data points. They go from 10 to 55, 65. They have actual data points. And instead, I'm saying I'm going to censor the data, middle censor, with some intervals. What do these intervals do? They cover up my data point, actual data point. And if I do this, over 23% of data were censored, resulting in just 157 uncensored observations. This is a practical example, I say on the top, practical application. So I did a trivial example with 5 data points, and then I did a simulation. And now this is a real practical example where we did some censoring, and 23, so 157 points are uncensored. So what happens to the other points? 205 points are there. So the others are all censored with intervals. And then the EDF and SE is superimposed. See this? This is the EDF. The EDF is the empirical distribution function with the complete data and the black line. And this SCE is the one that I get through my technology. If you can tell the difference between these two guys, you have very sharp eyes. They are that close. So the censored data with my technique can get you very close to what you would get with the entire data. In fact, the maximum distance between Fn minus Fn hat is 0.06. The empirical distribution function based on the full data and based on the censored data through the technique that I described. So maximum relative distance turns out to be 0.153. So that's interesting. So the story is, this is where, and we also established the strong consistency of Fn hat under some regularity conditions. We show Fn hat t minus ft goes to 0, it's probability 1. And then we have also weak convergence of the process. These are things that are individual papers that take time to explain even. So what is the point? That Fn hat again is the one that I get through middle censoring with some, some points hidden, some point not hidden. And then that minus the true F, the we can show goes to 0 on the almost surely. And then it's probability 1. As well as the result on asymptotic distribution theory, weak convergence of the process of this kind. Okay, now here are some of the things that some of my students did. I thought I'll throw it at you. Not all of them are students. My name is associated with most of them. Various parametric models have been investigated under the middle censoring scheme. What are parametric models? Where you start with exponential distribution, for example. There's a parameter theta in it. And then question is, what is this in the exponential distribution? You apply the middle censoring technique. What does the estimates that we get, how do they compare with the uncensored case, the true values, and so on? This is myself, SRJ, and Shrikant Iyer. He is a professor at IISc Bangalore, Indian Institute of Science. And Kundu is a professor at IIT Kanpur. Kanpur, that's correct, yeah. And SRJ Mangalam is a professor in Australia. We worked on circular data. You remember I drew a picture for you, a bird going away, and then it's missing if it went behind a cloud, except we know it's in between the clouds, in between the two endpoints of the cloud. And these guys worked on discrete lifetime data with geometric distribution. This is a student of mine named Leong. She is in Brunei. She is a professor there for discrete lifetime data in the presence of covariates. And this is another paper, Shrikant Iyer, the same guy in Bangalore, and Bennett. Bennett is one of my students for gamma and Weibull lifetime data. Shankaran is a professor at Cochin University of Science and Technology. And Prasad is one of his students. And we worked on semi-parametric regression model for middle censored lifetimes. Okay. SRJ and Bapat. This is for the multinomial model. This Bapat is just joined IIM Indore, I believe. He was a student. He was with me at Santa Barbara, and his dad was a professor at ISI Delhi. Any case, so we just finished this, and this is in statistics and probability letters. What is this multinomial model? This is something interesting. You know, you go to Amazon.com, right? And you buy some item, and they say, give it a rank of 1, 2, 3, up to 5. 5 stars, 2 stars, 3 stars. And whether to give you 2 stars or 3 stars to this. I'm split between 2 and 3. That's called middle censoring again. So it's like you have an interval, but in this discrete set of 1, 2, 3, 4, 5, you can decide whether to give this item a rank of 2 or 3. So you say, I give between, I give an interval 2 to 3. That's called interval, same middle censoring. And this paper appeared just recently in multinomial model. Multinomial model, because if you have only 5 items, five ranks that you can give, you give either score 1 or score 2 or score 5, P1, P2, P5. That's a multinomial model, and then you have middle censored in there. And here are some references. I'm at the end of my talk now. Brad Efron has a paper on the related topic to sample problem. This is the guy in Curtin University in Australia, non-parametric estimation. This was one of our original papers. And this is a paper with Shrikant Iyer. Shrikant Iyer is the guy at ISC Bangalore. So Devashish Kundu is in IIT Kanpur. Sudeep Bapat is my, the guy who worked on multinomial distribution with me. And these are some of the other related papers. Kaplan Meyer is the starting of this kind of discussions, non-parametric estimation from middle censored data. And these are double censoring and so on. I thought I'll throw in some references here. And that's the end of my talk. Okay, I think that's the last slide of mine. And these are some of the references for the talk. And I appreciate your listening to me. Thank you. Questions?
Sir, Umashankar garu.
Can I start then? Umashankar garu, మీరు మ్యూట్ లో ఉన్నారు.
Sir, Umashankar garu.
Umashankar is muted. So maybe Yadavalli can ask me some questions.
Yeah. Namaste, sir.
Okay.
Rao garu, namaste.
గురుగారు సార్ గురుగారు ఒక్క నిమిషం ఇక్కడ ఒక 3-4 questions from the participants are there because they are young and all.
Okay.
And then you and me can just have some 1 or 2 questions too, sir.
Okay.
Okay, Gurugaru, with your permission.
Yes.
Sir has presented in a very manner the middle censoring problems, and he has successfully encountered the non-parametric MLA estimation in order to find out some of the solutions for very practical problems. So he has given what is basic definitions of left and right censoring and what is middle censoring and all this. Sir, before I just put forth the participant questions, I have one small, what we call as a proposal, because basically I did some reliability studies. The mortality rates, sir, the age at which the death, the average age by the total population. So when you take an interval, sir, whenever the decision makers, as far as particularly life insurance corporations, they come up with so many policies. So whenever I join at the age of 25, 30, 35, there are many policies that the age, generally they take the starting age and the average age at that time, that can be taken as RI, sir. And this can be the age at which joining is LI. And the probability of survival in between. People who are going to be less than LI, no problem, who are going to survive more than RI, sir. So in between, as far as your example is concerned, once you are taking some 22 and 78, there are
Right.
live participants of 78, sir. So there is every possibility that the survival between Li and Ri once again a random variable. And
Right.
supposing that if you are able to estimate through these sort of studies, that can be very useful for the decision makers, particularly in insurance studies, in order to
Yes.
come up with policies such that they are able to make some sort of, say, the equilibrium, not undergoing losses, but also to help the, say, the contributors who are joining the policies. It is
Yes.
a sort of a survival analysis in between the intervals.
Yes. That's absolutely correct. In fact, yeah, this is exactly the context in which you have only intervals in which they fall. So we don't know where they fall. So you don't want to ignore that information. So we are trying to say that's why we call it a middle censoring. And yeah.
So the first participant question, sir, how exactly to use this method when the patient lives in between the study? I repeat, sir, how exactly to use this method when the patient lives in between the study?
Yeah, yeah. So that is, if a patient leaves the study, that is called right censoring. That is where Kaplan-Meier estimator works. There's a special case of what I am discussing right now. What typically happens is a patient is in the study and he or she leaves the study. So we know, of course, he's alive. He or she is alive at that point. So we know his or her lifetime is bigger than that point of departure. So that's called a right censoring, and that is Kaplan-Meier estimator is the standard tool, and this has been famous, very famous for a long, long time. So ours is a generalization that when the patient dies is not exactly known, but it falls in a certain interval that you know. That's what we are able to tackle. So I said to you, I said that this is a more general case than the Kaplan-Meier estimator.
The second question is, this will help me to make use of data collected on patients who have left in between before the study is completed.
Right, right, exactly. This is a beautiful tool. In fact, not only if they leave the study, this works for sure, but it also works when they go away for a short time. And for a short time, the hospital is closed, for example, in a study, and then you don't get to see exactly when this happened. Yeah, some events happen during that period.
Is there any relation between Li, Ri, and rough set theory, or is approaches to rough set theory is applicable?
Yeah, no. Li, of course, is the left limit. Ri is the right limit. So Li is smaller than Ri, but they can have any joint distribution between themselves. Li, Ri have a joint distribution, and that is what we call a nuisance parameter. We don't want to get involved with that, but we still try to estimate the original X data points. X's are the original lifetimes. So this is that LR distribution of the L comma R is what we call a nuisance parameter, and we try to overcome that, estimate life values X.
Is the interval censoring different from middle censoring?
Yeah, you see, interval censoring idea has been used in a lot of contexts, but this is a little different. I would not. I think I had 2 slides explaining the difference between various interval censorings. But interval censoring is oftentimes where people are coming every morning and checking if their light bulb is gone or not gone. So they know each day whether a bulb is gone or not gone. So that is often called interval censoring. You come every morning, you see how many bulbs are, put 100 bulbs to run, and then you see if a bulb is gone, they come back next morning, come back the following morning. So you observe things in between intervals. And there are several notions of interval censoring. I could get into great detail, but yes, is related in some fashion.
I invite Professor Yadvalli.
You are muted.
Oh, thank you, Umashankar garu.
Guruji,
Rao garu,
my name.
maybe one of the students have, one of the candidates have asked that question, whether we can find the distribution between Li and Ri, the joint distribution, even if it is a nuisance parameter, can that be minimized?
I think I'm saying that the LI-RI distribution can be any arbitrary distribution. And my goal is not to, in this particular kind of work, my goal is not to worry about what the distribution is what I call a nuisance parameter. The distribution G that goes with L comma R is a nuisance parameter. It's just bothering me. I'm mainly interested in the survival values, Xi's. The only thing is Xi's are hidden in between L comma R. So I'm not interested in estimating LR, but I'm sure it's possible also. Yes, in fact, it's possible. In fact, we have a paper where we do estimate the joint distribution of X comma L comma R.
Yeah. Okay. I have two other simple questions, Rao garu.
Cheppandi.
Yeah. Li, you assumed, of course, in your example, it is assumed to be an exponential distribution. And then you have done both the simulation as well as the data for the Odense hospital in Denmark, whatever.
Right.
Yeah. Now, has it been extended to the other exponential family distributions?
Yes, in fact, the students of mine, let's see, this Leong has done discrete lifetime data, so they use a geometric. I think this student of mine, you see, Weibel gamma and Weibel lifetime data. This Bennett is one of my students. Srikant Iyer is from Bangalore. Yeah, this is a. So we can use any parametric model, whatever model you want. Yeah.
Okay. The last one is the data is in the public domain, or is it one has to purchase, or what is the hospital data you have collected?
The hospital data, I forget now, but I think it's actually in a book on survival analysis. It's publicly available for sure. Yeah, it's a very well used data set. So they didn't have any censoring, but we applied censoring and showed we do as well as with censoring as without censoring.
Yeah, because sometimes we get a real data is a problem. So
correct.
Please take from the Thank you very much.
Thank you.
Anybody else? Tirupati Rao? He's not here. Sir, one thing maybe I recall my late Professor MP Shastriji. So I am a student of OR basically, without much knowledge and my statistical.
Sir, excuse me, sir.
And during my MP classes, sir, he has been speaking and teaching us these censoring models and censoring type of distributions and what is left censoring, right censoring. Maybe after 40 years, sir, it is once again a learning process from you, sir,
today. Yes, that's true. Parai Shastri worked on censoring problems.
Yes, sir. He has done a lot on this and also on dam theory models.
Correct.
Yes, sir. So over to Dr. Sridhar.
Okay. Sir, Professor Krishna, sir, good evening, sir.
Good evening.
Sir, kindly stop your presentation, sir, so that we will take the virtual photo, sir.
Okay, let's see. I go
with all legendary statisticians.
I go to stop share. Okay. Yeah.
Okay.
Let's see. You see my beach, huh?
Yes, sir. It's a wonderful, wonderful house to live in.
Background. It's a free background from somewhere.
Yes.
Okay, sir. I thank Professor J. Srinivasarao Garu for his excellent talk, and also Professor C. Umashankar Garu for chairing this session.
Thank you, sir.
So let me propose the formal vote of thanks. I have a whole lot of list here.